Can you think of some other subspace in R2? Probably every line through the origin is a subspace. This was one of them. I fix x naught. X naught could be anything, right? So that is another possibility. That means R lines passing through the origin in R2 are vector spaces in R2, right? Some other example. So I am just looking at R2, simple one we can visualize. So let us look at another example. Let us look at the 0 vector alone. So that is V. Is that a vector space? Yes, only one element is there. Whatever you multiply, it will always be 0 and it will be staying inside. So is a subspace. Oh, sorry, is a vector space. Let us look at the whole space plane. So let us look at third example. V equal to R2. V is a subset of R2, right? V is a subset of Rn. So I am just looking at specializing n equal to 2. What about V equal to R2? Is that a vector space? Yes, it is, because if I take any two vectors, right, multiply alpha, so right, if V1, V2 belong to R2 and alpha, beta belong to R, does this imply that alpha V1 plus beta V2 is again in R2? Yes, it is a vector again, right? So V equal to R2 is a vector space. So in R2 or in Rn, so you can write generally in Rn, look at the 0 vector and look at V equal to Rn. These are always vector spaces, right? So these are called trivial vector spaces. You don't have to verify anything, they are obviously given, right? They are obvious examples of vector spaces. Interesting thing becomes when you want a proper subset of Rn and you want to say it is a vector space. So interesting thing is V proper in Rn and it should not be equal to 0, because 0 is always good, right, is a vector space. When is it a vector space? So the examples I have been trying to give you are in R2, every line passing through origin is a vector space. 0 origin itself is a vector space, 0 vector. Whole of plane is a vector space. You can ask a question, is there any other subspace? Is there any other vector space in R2? Is there any vector space in R2 other than 0, other than the line passing through origin and the whole space? For example, let us look at this. This is interesting example to consider. So look at a line not passing through origin. So L, which is a proper subset of R2, a line not through origin. So question is it a vector space? So that is the question. So is it a vector space? So how do you describe a line as a set of vectors? So I can write this line L as, I want to write set of vectors in R2. So how we have been writing the vectors? Normally points in R2 are written as the ordered pair x comma y. You can write also as matrices, right, column vector x comma y, whichever way. So let us write it as a points for the time being. It is x comma y such that, what is the relation between y and x if they have to lie on a line? Right. So y is equal to some mx plus c. right, for some m c, and if you want not through origin, then c should not be equal to 0, right. So, that is all points on the plane which lie on the line are given by these two constants m and c. So, I want to check, right. So, whether if I take 2 points here, whether the combination, right. So, as vectors what you will write x1 y1, other vector would be x2 y2 on the line. So, let belong to L, and let us take alpha and beta belonging to R, then alpha of x1 y1 plus beta of x2 y2. I want to check whether it belongs to L or not. What is that equal to? By our vector addition, that is equal to alpha x1 plus beta x2, and here it will be alpha y1 plus beta y2, right, vector addition. So, now let us go a step further and try to simplify this. What is the relation I know? So, we know what x1 and y1, x2, y2 they belong to L. So, what is y1 equal to mx1 plus c1, what is y2 mx2 plus c2, right. So, given this, is the following true, that means alpha x1 plus beta x2, right, that is x squared. So, whether can I say m times this plus c is equal to alpha y1 plus beta y2, is that okay? If this point has to belong to L, then what should be the condition? The y component should be equal to m x component plus c, right. So, can I say this is true then, right. So, what is this? So, this is alpha of mx1 plus, I don't, do you think, okay. So, let me just ask you instead of saying, do you think this will be true? Because what is y1? So, what is the right hand side? Let us look at the right hand side of this. What is that? Alpha times y1. What is y1? x1 plus c1 plus beta times y2, that is m x2 plus c2. So, what is that equal to? So, that is alpha times mx1, okay, alpha times mx1 plus alpha times c1 plus beta times mx2 plus beta times c2. So, I can write this as, right. So, so I want whether this is equal to this one m alpha x1. So, whether this is we want to know whether this is equal to this y1 y2 is equal to m times alpha times this is y1, this is alpha y1 plus beta y2, that is equal to this, that is the right hand side, is equal to the left hand side. What is the left hand side? Alpha m x1 plus m beta x2, no, there is no m alpha plus m beta x2 plus c2. So, well, we want to know whether these two are equal or not, right. So, do you think they are equal? Where is C? Yeah. So, that is C, right. See, left hand side is alpha m x1 plus beta m x2 plus C, right. So, what happens? Alpha m x1 I can cancel out this, beta m beta x2 I can cancel out this. So, that means this is asking for, is it true that alpha c1 plus beta c2 is equal to C? for every alpha beta, right, then only left hand side will be equal to right hand side, but that is not true for every alpha beta. For example, alpha I can choose 0, beta I can choose 0, that means C should be 0, but C is fixed, that is given to me, I can't say it is 0, right. So this may not happen always. So that means what? So that is a contradiction, not possible always. So what does that mean? That means, what is the conclusion? So the conclusion is that if I take L equal to xy, where y is equal to mx plus c, c not equal to 0, okay, then L is not vector space, then it is not a vector space, because if I take two elements and take scalar multiples of them and add, that is not again in the same, right. So that means in the plane, every line through the origin is a vector space, every line which is not through the origin is not a vector space, right. So the question still remains, can I say these are the only subspaces, or these are the only vector spaces in R2? I can't answer that question at present, but that is a true statement. So we will show later, right, these are the only vector spaces in R2, either it should be trivial, that is 0, or it should be the whole space R2, or it should be a line passing through origin. At present we have only shown these are vector spaces and no line not through origin is a vector space, but we will say these are the only ones a bit later, okay, right, okay. So line passing through the origin of slope, and now this is an observation. We said if a line does not pass through origin, that is not a vector space. In fact, that is a property of every vector space. That means if V is a vector space in Rn, then the 0 vector should be inside it. Why? Why should 0 vectors be inside every vector space? So what is the definition of a vector space? It says alpha V1 plus beta V2 should belong to V for every V1 V2 in V and alpha beta scalars. But who stops me from taking alpha equal to 0 and beta equal to 0? That means the 0 vector should be in V, right. Alpha V1 plus beta V2 should belong to V for every alpha beta and for every V1 V2 in V. In particular, if alpha equal to beta equal to 0, then what is alpha V1 plus beta V2? That is 0. So 0 should belong to V, right, otherwise it is not true, right, that property says. So that means it is a necessary condition for a subset V in Rn to be a vector space that 0 must belong to it, otherwise it cannot be a vector space. So that is what happened in the plane. No line which is passing through the origin, that means if a line is not passing through the origin, then the 0 vector is not part of it, so it cannot be a vector space, and that is what we proved, checking actually, right, okay. So let us start with some finite number of vectors in Rn, okay, and scalars are, and look at this new vector alpha V1 plus not alpha C1 V1 plus C2 V2 plus Ck Vk. So what I have done, I have scaled every vector V1 by C1, V2 by C2 and so on, and taken a sum of them. That is again a new vector, right. So this thing C1 V1 plus C2 V2 plus Ck Vk is a new vector in Rn. So such a vector we will call as a finite linear combination of V1 V2 Vk, just a name. Why finite? Because the number of vectors is finite, you can just call it as a linear combination, okay. But to stress that we are taking only finite number of them, we will just say finite linear combination of these vectors. So now comes a general definition. What is happening? Okay. So let us look at a set. This symbol has not come out. S, a subset of Rn. Look at a subset S of Rn. Now what I can do? I can pick up any finite number of vectors from S and form a linear combination of those vectors, right? So I choose any vectors v1, v2, vk in, right, in S, and look at scalars c1, c2, ck in R, and form a so where are these v1, v2, vk? They are coming from, right, from the set S. So that should have been written here. Pick up v1, v2, vk in S, scalar c1, c2, k in R, and look at this linear combination and make a set consisting of all these linear combinations. Call that as LS. So what is LS? LS is the set of all finite linear combinations of vectors taken from S, right? Is it clear? This K is not fixed. K is not fixed. You can pick up only one vector. You can pick any 2, any 3, any 4, any finite number of them. Form a linear combination by picking vectors, finite number of them, picking finite number of scalars, making a linear combination. Form all such possible linear combinations, right, and call it as L of S. For example, in that example in the plane, we took a fixed vector x0 and multiplied alpha by it. So we took all linear combinations of the one vector. S was only a single vector. That was a line, right? So this is called a linear span. LS is called a linear span of the set S. Set S is a set of vectors. It may not have any property, right? You pick up elements from S, any finite number, form a linear combination, you get a new set, right, of vectors. That is called the linear span of the set S. So that is denoted by L of S. The theorem is LS is always a vector space. S may be any set, but LS is always a vector space. So let us check that why it is always a vector space. It's a simple proof, but let us check it. Okay, right. So S is a subset of Rn. What is LS? LS is C1 V1 plus CK Vk, right, where V1, V2, Vk's they belong to S, and C1, C2, Ck's they belong to R, and K is not fixed. So K is any natural number, that also varies. Is it clear what I am saying? We are not choosing only K vectors, we are choosing K is anything. I can choose one vector, I can choose 2 vectors, 3 vectors, right? Any finite number of vectors, form a linear combination and put them in a box, and that box is called L of S, right? So the claim is L of S is a vector space. This is a vector space. So let us verify. So what we have to verify, right? So what is the proof? How do I verify this? To show it is a vector space, what I have to do? Take 2 elements of LS, take scalar multiples of them and add, that should again be in LS, right? So let us write, so let one element, let us call it as a vector x, be equal to sigma. So instead of writing dot dot dot, we will start using this notation, sigma, it is Ci Vi, I equal to 1 to some n, right, where Ci's are real numbers, Vi's are vectors in S, right? Is it okay? Let us take another vector y, which is something, some other scalars say di, w, dj, wj, j may be from 1 to m, we do not know from where to where, right? They may not be same vectors chosen again. For y, we will be choosing some other vectors, some other m number of them. So, where dj's belong to R and Wj's belong to S. So that is what is given to us. So this, what we have to check? So check, or let us write then what is alpha x plus beta y. Then for alpha and beta belonging to R, I should add them and check. It is again a linear combination, right? But what is this equal to? This is alpha times I equal to 1 to n Ci Vi plus beta times j equal to 1 to m dj wj, right? But what is this? This is same as I can take alpha inside. So this I equal to 1 to n alpha Ci Vi plus sigma j equal to 1 to m beta dj wj. Is that okay? But what is this? That means I have chosen vectors v1, v2, vn up to vn. I have chosen also vectors, right? So my new collection of vectors is probably n plus m. Each one is multiplied by some scalar and added. That's all, right? So is it clear that this belongs to LS? Yes. It is again a linear combination, finite linear combination of elements from S. That's all, nothing more than that. Right? It is a matter of only writing. So this is okay. So hence L of S is a vector space. L of S is a vector space.